and let L be the number of particles passing per unit time per unit area. Number of particles per unit time per unit area. So then the infinitesimal number of particles L d sigma. Now, this d sigma is the infinitesimal area. So this is just by definition infinitesimal area. And this can again be related to some this infinitesimal area is the area where this particle will pass through. Then you can write Dn equal to L d sigma, and you can write this in terms of a solid angle d omega. Now, so this sigma now, that area is some function here multiplied by the solid angle, because typically this area is not two-dimensional but a solid angle. So you will see that therefore d sigma d omega is called the differential cross section. It's called d theta, and this is 1 over L and d omega. So this is called the differential cross section, which you learn in advanced physics. And that differential cross section, for example, for Rutherford scattering, which is Rutherford scattering actually is a Coulomb scattering. It is, for example, alpha particle scatter from nucleus. And why the alpha particles scatter from the nucleus? Because alpha is positive. It has 2 neutron, 2 proton. So obviously it is, because of the proton there, it has charge of 2. And then when it scatters from the nucleus, why? The nucleus have a Coulomb barrier. So, because there are protons inside the nucleus as well. So that's why it deflects. So positive deflected by positive. Okay. But this Rutherford scattering is only for less than about 27 MeV. Once you go beyond that energy of the alpha particles start to interact with the nuclear force itself. Start to touch the nucleus, not scattering. Tadi itu repulsion, isn't it? But now because it is very energetic, it go very near to the nucleus and start to interact with the nuclear forces. So the Rutherford formula at higher than 27 MeV does not work, because there is something else, an extra interaction there due to the nuclear force. So that's why you have to keep it at below 27. This one gives the d theta, or differential cross section, as Q1, Q2. Why Q1, Q2? Because Q1 is the alpha, Q2 is the charge of the nucleus. 4E, the energy of the alpha, sine square theta over 2 whole E square. So basically this goes as 1 over sine to the fourth theta over 2, where theta is the scattering angle. Okay. Now, then we now go to the golden rule, point number 2. Now, so now in any scattering problem, okay, you need to calculate of course this scattering. If the energy become very high, it become a kind of not really scattering, but what we call inelastic scattering. They are elastic and inelastic. So once you go very deep, you can even have what you call a deep inelastic scattering. Okay? So it does not just scatter, but it also kick out some particle. It also interact and so on. Yeah? So the projectile might itself change into something else. So, but this generally called scattering. So in any scattering, we need to calculate two things at least. This calculation is very important because you need to design the experiment, and if you want to use something that high energy, for example like Large Hadron Collider, one experiment might cost you 10 to 20 million. Yeah? So in one single experiment for say 3 or 7 days, okay, to get some data. So cost you 20 million, for example. So if you don't do the calculations, you might waste the experiment. So the first thing is of course decay rate. Something interact, something form, and once that form, it starts to decay. Like say resonance, for example, formation of resonance, for example. And then of course scattering cross section. So that's normal. Why? Because from the scattering cross section, you know what is the probability of this interaction between A and B, and what is the so from there whether it is big or small, then it show the importance of what is controlling the interaction, because there might be something dominant, there might be something not dominant. So these are called branching ratio and so on. So and in both cases, you need two things. You need to know two things involved. Again, A and B, there is the amplitude called M for the process. So this M actually is in quantum mechanics an easy calculation or easy handle is typically using matrix, okay, some matrix. So that's why you have the Pauli matrix, Dirac matrix, and so on. And this even for isospin and so on, they are all in terms of matrix form in interaction involving what do you call it, mixing of this quark. You have the CTM matrix and so on. So M in general is a matrix, and of course then number 2 or B here, the phase space available. This is a more what you call abstract. This concept of phase space is abstract. For example, at very low energy, you want to do XRD, X-ray diffraction. So how do you relate the scattering angle with the lattice size of, for example, the crystal that you are looking using X-ray diffraction? So the distance between the lattice or between the atom, these are measured in angstrom or maybe nanometer. Okay, these are real scale, nanometer, angstrom, micron, and so on. But the scattering is in angle, and in wide angle there are no energy losses, but at low angle you can have large energy losses of the X-ray, because wide angle involve just a kind of diffraction. Okay, diffraction at wide angle, you have no losses, whereas at low angle, the particle that you want to see is become bigger and bigger, and they can absorb the X-ray. Okay? So that actually, so the angle basically define the phase space. Okay, there are some angles you don't see.